No rats. Okay, this is a continuation of the prior video, which I wish I could merge the two together. Not really sure how to, so pretend that this is the part 2. Okay, start off with G of S being 150 over S squared plus 30S plus 200. Came through G of J omega, got the magnitude G of J omega like that. That's perfectly satisfactory form to put the answer in. While we're at it, magnitude G of J 10, okay, is going to be equal to what? 150 over 200 minus omega squared is going to be 100. 100 squared plus 30 times omega is going to be 300, or J being 10. So that'll be 300 squared, so 0, and the square root of all that. All right? And so if we evaluate this, then we're going to get as an answer let me make sure I got that right. Yep. 0.4743. All right. So we got G of J10 like that. What about the angle of G of J omega? That's going to be equal to the angle of the numerator, which is 0 degrees minus inverse tangent of the angle of the denominator, which is the inverse, the angle of the numerator minus the angle of the denominator. Denominator is going to be inverse tangent of 30 omega over 200 minus omega squared, like that. This is equal to, let's see, well, that's it. That's our expression, minus inverse tangent of 30 omega over 200 minus omega squared. All right. Now, we can go ahead and plug in then our value for 10 radians per second. Angle G of J10 is going to be equal to minus inverse tangent of 30 times omega is 300 divided by 200 minus that, so that's 100. 200 minus omega squared is equal to minus inverse tangent of 3. I did actually condense the two there. I've got the same positive values, the numerator positive, denominator positive. And so the angle of that is going to be, can I buy 71 degrees? Sure. Except it's going to be negative, of course. I go one part over, and I go 1, 2, 3 up. That angle, I buy that that's about 71 point, what did I say there, 57 degrees. And so I got to remember that I'm going to use that, so the angle of G of J10 is going to be equal to minus 71.57 degrees. Now, just to try to hammer home that point about the phase angles when we go beyond negative 90 degrees, the angle of G of J20 is going to be equal to minus the inverse tangent of, the numerator goes 30 times omega. 30 times 20 is going to give us what, 600, divided by 200 minus 20 squared. 20 squared is going to be 400, is equal to minus the inverse tangent of 600 over minus 200 is equal to minus the inverse tangent of, what's it going to be, 3 over negative 1. Now, I did actually factor them out because I kind of have an interesting symmetry going on in this case. I suppose that's because, why is that? Not real sure. But what we've got going on then is I've got 3 over negative 1. I could go ahead and put my negative inside there and recognize that I'm in the third quadrant. I'd really rather not. What I'd rather do is go ahead and recognize that, okay, if I'm over like this, and I go over 1, that's my negative 1, and I go up 1, 2, 3, I'm going to be at this angle, which is taking this and it's wrapped about 90 degrees in that direction. So what we have right here, over on this side, this is going to be 71.57 degrees. If that was 3 over 1 is over there, then here we go, that's 71.57 degrees. So this side is equal to 180 degrees minus 71.57 degrees. Is equal to what? That's going to be essentially what, 109 minus 0.57, so 108.43 degrees. Okay, that's this angle. And so this angle down to here is going to be minus 108.43 degrees. And I got to get this phone call. So, hi, hang on just a second. I got to hit pause on something. All right, back to it then. So the point there is, again, if you think about what you're doing when you get the phase angle, you think in terms of the complex plane, you think about these angles and which quadrant you're in, then the answer's not all that bad, not all that difficult to get. But you got to do that. That's the key element there. It's a step-by-step process. Yes, there are ways of recognizing to have to take shortcuts, but to be honest, in many years of doing this, I've never bothered to do that. I very much prefer to think about it as a step-by-step process. When I go through, I evaluate the numerator, the denominator. I look at the sign of the numerator and the denominator. Yes, I can do a little bit of canceling some common factors there, but I'm going to leave that bottom. If that bottom's negative, I'm going to leave it negative. This is not the same thing as saying the inverse tangent of -3 over 1. They have relevance. This is where the sign is. So let's see, that was problem 4. 2 to go. Now the next two are kind of interesting because the phase in the numerator on the next two does not go to 0. And the magnitude is a little more interesting. Not a lot, but a little bit. So let's do those. We actually have a 0 in the numerator, is what this is called, in number 5. It's 104s over s squared plus 20s plus 104. What's interesting about this is that the magnitude, or the step response, actually will be 0 at steady state. It will bounce a little bit and then kind of come back down a little bit. I know that because the constant term up here plus 0, the s to the 0 term is 0 at steady state for step response. We can use that final value theorem that I did talk about in class. We can use the final value theorem to recognize that the limit. All right, limit as s goes to 0 of s g of s is equal to g of t. No, s x of s is equal to x of t is equal to infinity. No, I'm not going to test you on this, so you don't have to go panic and go searching it all up. I'm just telling you, this is a really interesting approach, and so for us, limit as s goes to 0. If this is the transfer function g of s, which is equal to x of s over f of s, for example, the output over the input, then we multiply s times x of s over f of s. A step input means 1 over s times g of s. Like that, we cancel those two out, and so it's the limit as s goes to 0 of g of s is equal to, oops, little x of f. That's for a unit step response, a unit step input. If we have an amplitude a as a step, then we would have to say, whoops, that's not there. It's a times g of s, but what you see is that as s goes to 0 in this term, the denominator goes to 104, the numerator goes to 0. All goes to 0. Enough of that. It has what's called a high pass filtering kind of an effect. Gets rid of the DC offset. Anyways, g of s is equal to all this fun stuff. So g of j omega is equal to 104 omega j times 104 omega over a negative omega squared plus j times 20 omega plus 104. Yes, I'm kind of jumping ahead a little bit on some of these things. I went and implemented my j omega here, and I implemented it there, and there, relatively in the numerator. And so we can actually express this as 0 plus j times 104 omega divided by 104 minus omega squared plus j times 20 omega. Very similar to what we had before, but not the same thing. And so now the magnitude g of j omega is going to be equal to the magnitude of the denominator, the magnitude of the denominator, which is the real part squared, 0 squared, plus the imaginary part squared, 104 times omega, so it's really 0 squared plus 104 times omega squared, which, don't you know it, that's equal to, the denominator there is just simply 104 omega, Okay, that happens sometimes, not the next problem. Okay, so we're still kind of leaving it alone. Now we have an omega that pops into the numerator magnitude, and the magnitude of the denominator then is going to be what we had before, 104 minus omega squared plus 20 omega squared. And so the final expression then, if we wanted to do this out, let's see, is equal to 104 omega over 104 minus omega squared plus 20 omega squared is going to be 400 omega squared, like that. I believe that's the answer that we have on here. It is indeed. So moving forward then, the magnitude GOJ10 is going to be equal to what we have, 1040 in the numerator, because we just plug in 10 there. We have 104 minus 100, so that means 16 plus 400 times 100, which is going to be 400 times 100, but we've already done this once before. The denominator is going to roughly be, like I said, 20 omega, so roughly 200, right? We're going to, if this is roughly 200, so 1040 divided by about 200, it'll be, now that's interesting. Yes, okay, good, I'm glad. I was going to say it's about on the order of 5. By my numbers, if it was just this, we get 40 divided by 200 is 1.2. Yeah, 5.2, and we actually get 5.19. Okay, close enough. So 5.199. All right, I think I did some shortcuts on that. So that's how we get the magnitude. Now the phase is definitely a little more interesting because the phase of the numerator is no longer 0. And you never know. I might ask a question like this on the test, just because it's good for you. You know, just like broccoli. Kind of. Maybe. All right. I happen to like broccoli. Okay. But anyways, real relevance to 372, huh? Enough of that. Phase angle, GOJ omega. If this is GOJ omega, angle GOJ omega is equal to the angle of, and let's write this in as a real and an imaginary part, 0 plus J times 104 omega minus the angle, let's do it like that, the brackets there. The denominator is going to be 104 minus omega squared plus J times 20 omega. Again, that's the phase angle of the system. This set of squigglies over here looks like omega, omega, like a Walgreens omega times omega. That was supposed to be 20 times omega. Now, what we have here is the up here, we need to think about that. The real part is 0, the positive, the imaginary part is 104 omega, and that's the angle. And it's not the negative of that, it is that angle. So this is actually equal to 90 degrees for the numerator minus inverse tangent of, we take the imaginary part, which is 20 omega, divided by 104 minus omega squared, the real part. And let's see if I got that right here. 90 degrees minus inverse tangent of 20 omega, 104 minus omega squared. Okay, so now what we should probably do is the angle GOJ 10 is going to be equal to, again, 90 degrees minus inverse tangent of 200 over 104 minus 100, okay, is about equal to, let's see, it's 90 degrees minus, we already found out, well, inverse tangent of 200 over 4, which we found was equal to what, 88.86 degrees. That's degrees. 90 degrees minus 88.86 degrees. And so our phase angle should be 1.14 degrees. Did I get that right? 1.146. Yeah, well, okay, so I did some round off someplace. Yeah, I must have done some round off on one of those problems, one or the other. Roughly speaking, a little over 1 degree of phase angle. You could go ahead and use the GOJ20 there, in which case you'd be subtracting something greater than just 88.86 degrees. So now you'd be something below 0 instead of 1.14, probably something close to negative 90 degrees, but not quite there. I would encourage you to try that. So, got magnitude GJ10, got phase GJ10. Moving on, last problem, number 6. And it just illustrates again, in number 6, pay attention to what you're doing, where you are, what it means. All right, maybe not so much what it means right now, but let's go ahead and do that. So G of S is equal to, let's see, 20S plus 1,000 divided by, I don't know why I made that one so big. I'm sure I had a reason for it. 2S squared plus 60S plus 400. So G of J omega is equal to 1,000 plus J times 20 omega divided by, and let's be careful here, real part is going to be 400 minus 2 times omega squared. That's it, that's our real part, plus J times 60 omega. That is the expression for G of J omega. And so now the magnitude G of J omega is equal to the magnitude of the numerator, which is the real part squared, plus the imaginary part squared, is the square root of that. All divided by the real part squared of the denominator, so 400 minus 2 omega squared, plus, leave off that J again, 60 omega squared. 60 squared is going to be what? 60 times 60 is 3,600 omega squared, like that. Now we can also put everything under one single radical. I think I did that on the solution. And also as 1,000 squared, of course, that's going to be 1,000,000 plus 400 omega squared, all that fun stuff. Plugging in the number then, G of J10, I'm not going to bother trying to do that intuitively or anything else like that. 1.613. What I mean is not going to do any back of the envelope calculations. Let's just live with the hope that you can use your calculator and come up with that answer. So that's the magnitude G of J omega. Let's do the phase. The phase gets to be very interesting for this one. Angle G of J omega is going to be the inverse tangent of the imaginary part of the numerator, which is 20 omega, divided by the real part of the numerator, which is 1,000, minus inverse tangent of the imaginary of the denominator, which is 60 omega, divided by the real part of the denominator, 400 minus 2 omega squared. Okay, and so if we plug in the angle G of J10, we should get the inverse tangent of 200 over 1,000, or in that case, we can probably go ahead and say 200 over 1,000, well, we'll simplify that. It is equal to the inverse tangent of 1 over 5 minus inverse tangent of 600 over 400 minus 2 times 100, so minus 200. So it's minus inverse tangent of 600 over 200, which is 3. Hey, we did that one once before. Wasn't that 73 some odd degrees? Or 71, what is it? 71.57 degrees. Of course, this will make it a negative. And so the total phase angle is going to be, let's do the inverse tangent of 1/5. Enter 5 divided by, I guess I should have done 0.2, huh? Inverse tangent of that is 11.3 degrees. Minus, and I said that one was going to be 71.57 degrees. Like that. And so what are we going to get? 71.57 minus 11 is going to be 60.57. 60.27 degrees negative. How'd I do? 60.26. I can live with that. So, on the phase angles, take it step by step. Think about what you're doing. You should get the answer correct. And recognize where you are in the plane, the complex plane. And that's that. That's homework 6 review.